right? So the last class of parallel computation we will introduce is synchronous computation. Okay, and again we will use the prefix sum and the linear equation solver as example to show you how what is synchronous computation. Okay, by definition, synchronous computation means that any computation that involve a synchronized point in your computation. And usually, as you could imagine, that happens for iterative computation. And you probably have a synchronous point at the end of each iteration, right? So it's actually a very commonly seen parallel computation methods, including GPU programming. In some sense, is also a synchronous computation, as you could imagine, because mostly we use GPU to accelerate the computation of a for loop. And again, in most cases, you have data dependency across those iterations. So you must have some synchronized point. You have to insert the synchronous point at the end of the iteration, right, in order to resolve the data dependency. So it's a very commonly seen form for parallel computation. Okay, and the synchronization point, right? There are many API could be used to insert this synchronization point, and some of them are explicit, others are implicit. So like barrier is explicit API you call, right, you use to in order to create the synchronization point. Because as we know, this is a mechanism that will basically, right, stop or block all the processes in the parallel application to this barrier point, right? So you have to wait until all the processes to reach that synchronization point before they can start computing again. Okay. So implicit, as we will see, usually because caused by those blocking communication, right? For example, you send a message to all other processes, or you send a message in a right in a loop, or you can think as your homework one, right? Your homework one is actually a synchronous computation because there is an implicit barrier, right? A synchronization point between those iterations. Okay, so you probably didn't call barrier, but you still has this synchronization point in your computation. Okay? No matter what, for synchronization, because you need to introduce those synchronous point, you will cause dependency among processes. So the side effect is that it's very common to run into the deadlock problem. As we all know, that's the problem when all the process have to wait for each other, right? And at the end, no one can continue its process. Okay. Okay. So by introduce this synchronization computation, we first just use barrier as example, right? Because creating a barrier itself is is a form of a synchronous computation. Okay, so the definition we have, we all know about the definition for barrier. So we know this is how we could create a synchronization point, right, in our program. Okay, and there are actually many different ways to implement a barrier. Okay, the most naive way is what we call the counter barrier. Okay, so the idea of a counter barrier is that you will keep track of how many processes reach the synchronization point, or call the barrier function code. Okay, and after you call the barrier, you will not return the result immediately. So you will force to block the process, and you will wait until the counter reach the number of processes in our right, in our payroll program, for example. Okay, so when right, so you will only return from barrier when all the processes code the barrier, when the count reach the number of processes you have. Okay, so this is what we call the counter barrier. So this implementation, first of all, it's a centralized implementation or design, because that means we should have a master, right, to hold this counter value. And so, and all the worker or all the processes need to communicate with the server in order to increase the counter by 1, right? And they have to wait until the until the master to broadcast the return message to all the processes in order to complete this barrier code. Okay, so this is right likely what we're going to implement it. Okay, and as you can see, usually we will have this implementation consists of the arrival phase and the departure phase. The arrival phase is to wait the message from those workers or processes. Okay, and after you receive, you will not return the message immediately. Instead, you will wait until he receives the message from all the processes. And after you receive all the processes, you will move to the departure phase by sending the message back to each of the processes. And those processes, after you receive the message from the master, right, it's a blocking code. So you will wait until he receives, then continue his rest of the computations. Okay. So this is a very easy implementation, right? However, it's not very efficient because, first of all, obviously the master will become the performance bottleneck. It has some scalability issue because the master has to communicate with all the slave processes at the same time. Okay? Secondly, this mechanism involved arrival phase and departure phase, and those two phases, they are not overlapped. Okay, so that's what takes more time. Okay, okay. So what could be a better implementation for barrier code? Okay, one of it is what we call the butterfly barrier. Okay, and the idea is as shown here. The message actually there's no master for this mechanism. Okay, and every process when it reach the barrier, it will try to send the message in an iterative way to other processes. And the communication pattern is showing over here. It looks like the fly of a butterfly, right? The wing of the butterfly. So that's why we call it a butterfly barrier, because this pattern in networking is known as the butterfly pattern. Okay, so we call it as a butterfly barrier. Okay, and as you can see, the pattern is pretty easy to understand. It's basically try to pass the message to its neighbor by increasing distance, right, from 1 to 4, right, to the degree of 2. Okay, and as shown over here, right, after log n iteration, right, if a process receive all the message you need to receive, you can backward trace to see that that means all the processes has reached the barrier point. Okay, so this implementation has no master. It coordinate among themselves in parallel, in a peer-to-peer fashion, and the computation time you need is just log of all of log n, right? So it is a better implementation than the previous one. The only downside is that actually, if you count the number of messages along the way, it's actually more than the previous implementation. But load balancing is the key for parallel computation, right? So you can see those messages are sent in parallel, and they are sent in different link, right? They never, you never pass the message on the same link. So the traffic on those links are, the workload on those network links are more distributed or evenly distributed. Okay, and every node, right, or every process, as you can see, you only receive 2 messages at a time, right? So it has a better scalability, right? Okay, so you can see that that's what we mean, right? All those messages are sent in parallel, so all the processes can determine whether it can break out from the barrier at the same time. Okay. Okay. All right. So it is a synchronous computation because you can see that basically you have to those iterations have to happen one by one, right? So you have to complete the first stage before you can move on to the second stage, and of course at the end is the third stage before the barrier is completed. Okay. All right, so we jump back to the deadlock problem, right? As we mentioned, or as you can see from the previous example, there are so many send and receive messages going on, right? And the message needs to be sent and received in a particular order in order to have a correct implementation. So as shown over here, right? If just more, if you have more, if you are more careless, right? You write it as send and receive in a incorrect order, then it could easily run into the deadlock problem we mentioned. Just like shown over here, right? If you trace the code, you can easily see that P0 will wait on P1, P1 will wait on P0, and P2 will wait on P1. So at the end, no one can actually continue their execution. So it is a deadlock. Okay. All right. So of course, we are not going to talk about how to avoid deadlock or solve deadlock. It's basically a responsibility for the programmer. So you just have to be more careful about it, right? And the best way is you are clear on the communication pattern you have. So make sure you implement it in the right way, right? And so that can avoid some programming mistakes. Okay. All right. So here we give some simple example to show what is a synchronous computation. And the first one is the prefix sum. And the prefix sum, as shown over here, right? You can aggregate the result in your previous, if you're given a data array, previous sum is try to aggregate your previous data items by some operation such as sum. Okay. And in the most naive way, like the sequential code over here, this is n squared complexity. Of course, I think this is not the most, this is not the best complexity we can achieve for sequential code. But anyway, this is just example, and then you can see this is n squared complexity. Okay. So how can we parallelize it, right, in a better way, right? And as showing over here, very much like the barrier, the butterfly barrier we just explained, right? You can use exactly the same pattern, communication or synchronization pattern, to compute the prefix sum. Okay. And the way is as showing over here, right? In the first iteration, every number just added to its neighbor, okay, with one distance away. But in the second iteration, we will add the prefix, we will add the partial sum with 2 distance away, right? So on and so forth. We will add the number, right, in a longer distance, increase the distance by the power of 2. Okay. So at the end, you can draw the line. If you back trace those line, you can see that it will give us the prefix sum result we want. Okay, and what's the complexity? All of log n, right? So this is way much better than n squared, and of course, it's still better than the best sequential code the complexity for the best sequential code. Okay. So, however, you need to be careful about this computation because not only it's an iterative algorithm, more importantly, here you have to insert the synchronization point between the iterations. Otherwise, you might retrieve the value that's not completed yet or from your previous step. So you will get the wrong number from other processes, right? So you have to, the result of step 2 is built on top of the result of step 1. So you have to make sure the result of step 1 is all completed from all the processes before you move on to step 2. So we have to insert a barrier, right, at the end of each step to make sure the data dependency is resolved. Okay. Right. So okay. So the synchronization computation we mentioned. This is just a quick simple code, right? So if you again, if you implement it in parallel, you simply need to just add the prefix sum, but the distance will gradually increase by the power of 2, and you only need a log of an iteration to complete it. However, you have to make sure all the processes has a synchronization point after each iteration. So what does that mean? That means in terms of the implementation, from your parallel program, you have to insert those explicit synchronization point, right? Like barrier. And in OpenMP, because we said there is an implicit barrier at the end of the parallel region or the for loop region. So you don't need to add any code, but there actually is the barrier exists at the end of each iteration. Okay. And in GPU, as you will see in the next week, there's also an implicit barrier. However, it's more complicated because the barrier only applies to a portion of your threads, and we will explain that later. Okay, so because it's a portion of the threads, so if you want a global barrier, you still need to call the sync threads API. Okay, so you have to know the hardware to know exactly whether you need to make the synchronization code or not. Okay. But anyway, for many SYNC processor, actually, because we know for SYNC processor, supposedly it's a synchronous computation, right? Because at the same time, all the processes can only execute the same instruction. So supposedly they are always synchronized. And for GPU, although it is based on SYNC processor, but it's, as you will see, it's not built on just a single SYNC processor, but a group of SYNC processor. That's why we said the synchronization only occurred at a single SYNC processor level. It's only a partial threads. Okay? If you want to synchronize across multiple SYNC processors, across the whole GPU card, you still have to make the synchronization code explicitly, okay, in your program. Okay? All right. So finally, we will introduce this. Again, we'll use this linear equation solver X example, but it's a general form, as you can see over here, right? It's not a triangular linear equation. Okay, it's a general form. So in this case, if we want to solve this problem, it's a bit more complicated, and a way to solve it is to use the Jacobi iteration algorithm. It's a well-known approximation solver to solve a linear equation in arbitrary form. Okay, and its idea is pretty much like deep learning. You try to guess first, and then evaluate the result, depending on how far the result from the actual real solution it will adjust its guessing and try to keep refining the guess until hopefully his evaluation will be the same as the real value or the real result. Okay, so in more detail, as showing over here, right? Given every row, we can derive this equation, right, to for any given x value, right? And the computation start with a guess by, say, for example, assign bi as the value for xi. Okay, the guess doesn't, of course, it matters, but for now, let's just guess it arbitrary by assigning the value of b to value of x. Okay, and of course, if you this is your assumption, right? You're assuming xi equal to bi, so you can use this to evaluate, right, based on the equation to do the evaluation and to derive the actual value of xi if the guess for other x is given. And supposedly, right, what you guess and what you derive should match to each other, right? If it's not, then we have to adjust our guessing value. And we can repeating this until what we guess is equal to what we derived. Okay. So as shown over here, because your derivation, right, what you derive from your guess is iteratively refined. So the xit, right, is the value we derive from the t iteration, and ti is the previous right derived value, and we want to make sure those values are close together. Okay, and the reason we want to be close because supposedly, right, this is the exact value for some variable x, and when we keep guessing and refine the result, you will see that the result will be very close if it gets close to the exact value, right? Because of course we'll assume, right, this guessing result will be in a convex curve. So if it become very smooth, that means we are close to the exact value. Okay, so the idea is we keep refining the result until there's no refinement or adjustment need to be made for our guess. Okay. All right. So this just illustrate the whole procedures. Okay. So as we mentioned, this is the equation, right, to derive each of the x values. Okay. And this is our guessing, right? So the superscript here, the upper value over here, is the iteration. And the bottom here, this number is the, right, which variable, x0 to x2. Okay. And initially, we just assign 2 to each of those variable. And as we mentioned, we can use that, right, to evaluate the variable for the value of each variable for the next iteration, right? And for example, based on this given input, what we get for the x values are 4 to 1. And then we can compare, right, the new value with the old value. And if it's far away, then we will use what we derive as the next guessing for the variable to try to derive the next value for the unknown variable. So we just keep repeating this until, as we mentioned, the x value between iterations are so small within some error range. Okay. Okay. So so obviously this is the computations consists of right, for loops. Okay. And it can iterate it until we reach some maximum iterations or some termination condition. And within each for loop, we have to compute the result or to evaluate the value for each variable, right? So since the evaluation for each variable is independent, so that means we can, of course, assign multiple processes to evaluate those values in parallel. Okay. However, between iteration, right, we have to derive the result from the previous iteration before we continue the next iteration. So again, between this outer for loop, we have to have a barrier, right, between those processes. Okay. So so here is the parallel code, right? So as we mentioned, right, the parallel code basically it has iterate through the iteration, and each iteration, each process have to collect the the value from all the processes in order to compute the new value of its own variable. Okay, and he needs to broadcast, right, or propagate the new value of this variable to all the processes. So only all the processes receive the result, then we can continue the next iteration, and based on the result from the previous iteration to derive the new value. Okay, so as we mentioned, it has to have a barrier at the end of each iteration. Okay, so obviously this is a example of synchronous computation. Okay. This is an easy case in some sense because we don't have a we have a barrier, or basically within an iteration, right? Every process can compute independently depending on the previous result. But in some more complicated computation problem, you might have dependency between processes, even in the same iteration. In that case, it will be much harder, right? And so, but anyway, this form of computation are the general form for GPU programming, because GPU programming most of the time is try to perform this synchronous computation. But you have to insert those synchronization points and avoid data dependency in order to utilize the GPU core efficiently. Okay. All right. Okay. So after we talk through those parallel computations, at the end, we will talk about load balancing, because it is a critical issue in all forms of parallel computation, right? No matter which form you have, you will always want to make sure the load is balanced. Otherwise, your computation time will be prolonged. Okay? So, so why load balancing is so important? Because in principle, right, for any parallel computation, the overall computation time is bounded by the last one, the last process, okay, the slowest one. So if you can balance the load, then you can efficiently reduce the overall computation time. Okay. And for load balancing, basically, we roughly can classify it as static load balancing and dynamic load balancing. And by definition, static load balancing means the assignment between the task and the processes are predetermined. Okay, predetermined is not the same word as fixed, because as you can show below, right, round robin, right, round robin is a static scheduling, because it's not only static but also fixed, because you assign the task in a specific order, right? However, randomized algorithm also belongs to static static load balancing. Randomized algorithm means you randomly assign a task to a process. However, that decision is irrelevant to the process itself or the task you assign. And so at the end, what happened is it will guarantee every process receive the same amount of assignment, but still the assignment, whether the assignment is completed in a shorter time or longer time, doesn't really matter. You only ensure every process receive the same amount of tasks. He just doesn't know which task it received. So even for randomized algorithm, it's still a static load balancing strategy, because this decision is irrelevant to the runtime status. Okay. Similarly, recursive bisection means, like divide and conquer. So you just recursively divide a task and assign to the process. Again, follow the same pattern, is statically decided already. Okay. So for static load balancing, usually it's easy to implement because it doesn't require any runtime information to make the decision. Okay, so that's why its scheduling decision and algorithm usually can be implemented in a very efficient way. Okay. However, the result usually not very good in terms of load balancing, because the load balancing result is depending on the actual runtime, and then there are many runtime. The runtime depends on many other runtime environments, right? Information and factors. Okay. For example, some of the tests may run longer, and some of the tests may run shorter. So if you want to make sure the load is balanced, supposedly you have to know the execution time in advance in order to come up with some static algorithm that can guarantee the load is balanced. However, that implies you have to predict the runtime, which is very difficult because, of course, you have to know the computation, you have to model the computation, and even harder is due to the fact that the computation time or the execution time, including the communication time. And the communication time usually depending on the traffic pattern. And you might delay due to the link congestion. And that could only be known at runtime. So at the end, as you can imagine, it's very hard to know the runtime in advance. So the static load balancing usually cannot consider the runtime properly. Okay? If we want to consider runtime, then that's what we call the dynamic load balancing. Because by definition, the dynamic load balancing means you schedule the task according to the actual task execution time. Whoever complete the first, you assign the next task first. So it's a very basic dynamic strategy. But as we explained, right, in OpenMP, it could achieve pretty good load balancing if you can gradually reduce the granularity of your task assignment. Okay. All right, so here we take a step further to explain or to introduce how a dynamic load balancing mechanism or algorithm can be implemented. Because in fact, it can be implemented in a centralized way, decentralized way, or even fully distributed way. Okay? The centralized load balancing, dynamic load balancing, is what we already explained when we talk about, in the previous chapter, right? Or in before, right? When we explained the embarrassing parallel computation, right? We already explained how a centralized dynamic load balancing can be implemented. It's a centralized solution because, as we know, you need to have a master, right? To take control of the work pool and to do the task assignment. All the decisions are made by the master alone. Okay? So that's why it's a centralized implementation. And as all the centralized approach, we know it actually has a scalability problem. So it's very easy. It's usually easier to be implemented. But if the scale increase, it may become the performance bottleneck. For your homework too, of course, you don't need to worry about the scalability too much because we don't have that many processes or nodes for you. So I would encourage you to implement it in a centralized way, just to make it simpler, and sometimes it will be more efficient, right? However, in a larger scale, you have to worry scalability. So you could try to implement it in a decentralized way. Okay, so decentralized means you could have a master, but you don't have only one master. So usually it's very easy to implement the decentralized solution. Okay, so as showing over here, besides the master, you have some submaster or mini masters. Okay, and the way to do it is you have all the tasks, right, are managed by the are managed by the master, and the master will dispatch a portion or a subset of tasks to its mini master, and the mini master is responsible for schedule the subset of tasks to the worker. Okay, so the master doesn't need to talk to all the slaves or all the workers at the same time. It only talks to the mini master. So it reduces the scalability, right? The scalability problem of the master, because you can control the number of mini master. So you can have fewer number of mini master. And each mini master can only need to talk to a subset of worker. So again, it's not 1-to-0, right? So it can reduce the complexity or reduce the the scale. Okay, all right. So this strategy is what we call the decentralized work pool. Okay? It's not centralized because we don't rely on a single point. Okay? But at the same time, it's not fully distributed, as we will introduce next, because still you have the role of master and slave. So you still need to have master. Okay? All right. So what is a fully distributed work pool? Okay. Fully distributed implementation is that every process basically is a peer-to-peer communication. Every process takes on the same role, okay, and takes on the same responsibility. So that means every process or every slave over here has a portion of the work pool. It's a local work pool. So aggregate all the work pool across all the processes will be the same as your centralized work pool. Okay, and so every process or every slave, of course, first of all, you will try to process or compute the task from his local work pool, right? But when its local work pool is empty, he will try to request the task from other processes from their local work pool. And so in contrast, if the work pool is too large, right, the loading is too high on some processes, he can send a request to other slave to balance the load, right, by giving some of the task from his local work pool to other slaves. Okay, so the load balancing can be happening across processes in a peer-to-peer communication fashion. Okay, so this is what we call a fully distributed solution, because there's no master in this computation at all. Okay. All right. So we explained the concept, and for implementation, actually, by sending the request, by who sending the request, right, trigger the load balancing event, we can divide it into two methods. One is receiver initiate method. The other is sender initiate method. Okay? The receiver initiate method means that the process that expected to be to receive the task will send out the request first. Okay, so what does that mean? In translation, that means if if a process has lighter load, right? He has less request, then he will try to request the load from other processes. Then this is a receiver initiate method. Okay. On the other hand, if you want to, if the request is used to push the workload out to other process, then it is a sender initiate method. So the sender supposedly will be the process with a higher load. Okay. So you can define your load balancing strategy either in this form or in the other form, right? One of it. You usually don't try to mix up together because one of the method is enough to define or to trigger the load balancing mechanism. Okay? So you can implement that in either way, but they actually will be more suitable for different system environment. In short, the receiver initiate method will usually works better if the whole environment, okay, is more highly loaded. Okay, why is that? Well, actually, should be less. Yes, yeah, highly loaded. Okay, because in a highly loaded system, right, most of the processes will not try to initiate the request, because if you initiate the request means you want more load, right? You want to receive the load. Okay, so if we want to minimize the messages in our system during the load balancing procedure, then we want fewer requests to be triggered, right? So in a heavily loaded system, only few requests will try to issue this method, and no matter which other slave you try to request it to, more likely they have higher load than you. So this communication or this request has a higher probability to be accepted. Okay, so that's why it's more efficient implementation. On the other hand, right, if it's a receiver initiate method and you send a request to someone that has even lighter load than you, then your request will be rejected. So you have to send the request again to another slave, and you have to repeatedly do so until you find someone has higher load than you. So this is less likely, right? Harder to happen in a more heavily loaded system, because in general most of the process has higher load in that case. Okay. On the other hand, right, if it's a sender initiate method, it will be better suited for a lightly loaded system, because in this case, majority of the processes has lighter load. So the sender initiate means it will happen to the one that has higher load. So when you try to push your workload to other process in a lightly loaded system, is more easily to do so, because most people does have a light load, right? Okay, so again, the same thing. So in this case, your request will be more likely to be accepted by other processes in a lightly loaded system. Okay, all right. So the implementation choice actually depending on the system loading. Okay, and the reason is we want to make sure if the request is sent out, you should have higher probability to be accepted. So we don't have to resend the request again and again. Okay, because in a peer-to-peer fully distributed system, there's no coordinator. So usually you can only randomly sample, randomly send the request to other processes. So you want to make sure the acceptance probability is high. Okay, but either way, both of those methods suffer from the issue that it might be more costly to balance the load, because the load balancing will happen gradually among those processes. Unlike the centralized load balancing, you have a master and you have a global view, so you can probably reach the balanced status in a fewer iteration. But in fully distributed environment, the load actually needs to be propagated one by one across those processes. So you might need more iterations until the load is balanced. So you probably cannot balance the load immediately like the centralized approach. So that's the trade-off or the drawback of fully distributed solution. Okay? So as you can imagine, only when you have the scalability problem, otherwise, only when you have a scalability problem, then that will force you to design and implement a fully distributed solution. Otherwise, a centralized solution usually is more efficient and usually is more easily to be implemented. Okay. All right. So here we give a real example for the fully distributed this algorithm, right? And the example we have here is the shortest path problem. Okay, and for the shortest path, I think most of you already know, right, how to compute it, right? It's an iterative algorithm, and basically you have to explore the shortest path along the way when you traverse those edges. Okay, and so one of the famous algorithms is called the Moore's shortest path algorithm. Again, this is not the fattest shortest algorithm for sequential code, because the best algorithm we know is digestion algorithm, right? But again, it's actually not that easy to be parallelized. Or when the digestive algorithm get parallelized, it actually have the same complexity as the Moore's algorithm. Okay, and what is the Moore's algorithm? The Moore's algorithm is basically repeating this computation on each of the vertex across every iterations. And what it does is, as shown over here, it's based on the observation, right? Assuming the current distance, right, from the source to vertex z is dz. This is what we know. Okay, we try to compare to the result that can be derived from its neighbor. For example, I is the neighbor of z, right? And in previous iteration, we know maybe the current shortest path we explore from the source to I is 4. So we can derive that if we use the shortest path from I and then add the distance from I to z, which is 2, right, to reach vertex z, then the distance the distance of this path is 6, which is smaller than 7. So that means we should update the distance, the shortest path from the source to z from 7 to 6. Okay, so basically we're repeating this comparison, right? Try to explore whether there is a shorter path from the neighbor of z, right? And so we can repeating this until we explore all the possible paths. Okay, So whenever this shortest path from his neighbor is updated, we have to re-examine his neighbor, see if that will resolve a shorter path to his neighbor as well. Okay. All right. So let's look at just first of all from the sequential point of view, right? How we can implement this Morse algorithm. Okay. And as you can see over here, what we will do is we'll keep an array, right, to store the current minimum distance from the source to each of the vertex. And we have a queue, right, that try to store the shortest path that we just exploded. And we will propagate that, right, to those vertex to examine whether there is a shorter path exist. Okay. So we can do this step by step. So at the beginning, right, we have a source. We start from the source point, okay, source vertex, and it will explode like we mentioned, right? Of course, the vertex distance is 0, the source is 0, and so we will add the distance to his 3 neighbor, right? Vertex 2, vertex 6, and vertex 7. And by the distance of 9, 14, and 15. And originally, if it's empty, means it's infinite. So after we examine this S, then we know we should update the shortest distance for vertex 2, 6, and 7 accordingly. Okay. So since the shortest path for vertex 2, 6, 7 is changed, so in the next iteration, 2, 6, 7 will be added to the vertex Q, and so that will trigger trigger us to evaluate the shortest path of vertex 2, 6, and 7. And let's take the vertex 2 as example. He will check his neighbor, that is 24. Actually, that's 3, right? So we will add the shortest distance 9 by 24 and gets 33 and update the shortest distance for vertex 3, right? So on and so forth. I guess you all know what will happen, right? And at the end, as you can see, the vertex Q, the task will actually be generated at runtime. And it was generated only when we explore or we refine a shorter path to some vertex. And at the end, when the vertex Q become empty, that means there's no more shorter path is discovered. So no more shorter paths will be generated. So the algorithm can terminate it. Okay. All right. So this computation is sequential. We know this is we illustrated in a sequential way. So how we can do it in parallel? One way to do that is imagine, right? You have set of slaves, and the vertex Q is our task pool, right? So we have to compute the task in the vertex Q. And we have a minimum distance as array. That is the result. We're going to collect it from those slave workers, okay? Those worker processes, okay? And just as we explained before, if it's centralized pool, we can implement it again by assign the initial task to those slaves. And whenever a slave is completed, it will ask for the next task from the master. But different from before, you can see that after the slave complete his computing task, not only he will return the result of a minimum distance that he updated, he will also return the new task generated from the evaluation, right? So you will insert the new task to the vertex Q. Okay? And the number of tasks he generated is a variable size, right? It depends on the evaluation result. Okay. So but anyway, it's the same as before. We will keep repeating this, slave and the master communication until the vertex task is the vertex queue is become empty. Okay, And because, as we mentioned, right, the amount of tasks that return from the slave is not a fixed amount. So if you implement it using MPI, the communication actually need to happen twice. The first communication probably is to tell the master how many tasks he will generate it, and then reserve the proper size of the message buffer, right, in order to receive the all the tasks you generated. So it's actually back and forth twice, right? You need two messages back and forth between the master and the slave in order to complete this the step over here. Okay. All right. So those are just implementation detail, right? Due to the API of MPI, you have to know the number of message you're going to send in advance. So you might need two communications. Okay. All right. So how about the distributed version, right? So that is a centralized work pool. If we want to implement a distributed work pool, what happened is, just as the same concept we explained, each process will basically handle one vertex. Okay, and this vertex, every process, what he needs to do repeatedly over time is try to receive the message, or he's waiting the message from his neighbor. Okay, and each process will generate a message to his neighbor when he discover a new distance, right? And so the computation happen on each process is very simple. It's simply try to receive the new distance from his neighbor and add that distance with the distance from his neighbor to his own, and then compare to his current distance. And if it's smaller, he will update his distance value and propagate and send his result to his downstream neighbor. Okay, if it doesn't discover a new distance or shorter distance, then he will not propagate the message. So there will be no new task get generated. So let's look at this illustration, and the code will be more clear. Okay. So as shown over here, right, the implementation is like this, quite simple. Each process just try to receive the new distance from some neighbor, and when he receive, he will compare with his own distance. Okay. Which is stored as Wj, right? So W here is actually the minimum distance array over here. But instead of you have a centralized array, this array will actually be partitioned and scattered to each of the processes. So each process will handle the vertex, the distance, the minimum distance of its own vertex. Okay, so this array, we still need it, but it will be scattered around the processes. Okay, and we don't need a vertex queue anymore because the task will simply become the message we send it out from each of the process. So as shown over here, every time we receive a new task, we compare with the current value, and if it's shorter, we will update it and send it out to his neighbor. Okay. And so that's why we can keep propagate the update event, right, until until there's no more messages propagated among those processes. Okay. All right. So this is the fully distributed implementation for the shortest path algorithm we just mentioned. And you can see there's no master at all. All the processes are just sending message among themselves without centralized coordination. Okay. All right. So the last part of this this chapter, we will introduce on Thursday is the question of how to determine a termination condition. It might seem simple if you have a centralized design because you have a master, so you can immediately identify whether it reached a termination condition. But if it's in a distributed implementation like we're showing over here, the work pool is distributed, scattered across all the processes. So to know whether the work pool is really empty is actually complicated because you have to coordinate among those processes in order to know whether the work pool is actually empty. Okay, it's hard because you need to consider network delay effect, right? Even so, right now the work pool looks empty. It may not be empty because, like in this example, the task is generated by the message. So if the message hasn't reached the destination, you don't know whether there will be a new task or not. So the network delay issue needs to be considered if you are a peer-to-peer or fully distributed algorithm. Okay. All right. So we will leave that to our next lecture.